Okay, thank you. Okay, so we're going to talk a little bit about Chapter 4, which of course is vector spaces. And what are the kind of things that, just kind of crash course overview, what do you need to be able to do in this chapter? Of course, you definitely need to know the definition. And that's that page that we worked through that has the axioms A1 through A10, right? Most importantly are going to be the first two axioms, which are closure under addition and scalar multiplication. I definitely want you to know examples of vector spaces. There is, of course, a lot of them. We have Rn, so like the first example, and then we have, let's say, Pn of R, polynomials of degree n or less. Let's see, we have the n by n matrices, Mn of R, or we can make the matrices any size, not necessarily a square size, m by n matrices. And then we also have the calculus functions example. So C of AB is a good example. So these are like the primary, like, big vector spaces that every problem is happening in. Okay? And you've seen this already, I know, in the homework and stuff. Like, so one problem will be about polynomials, and then the next problem will be about vectors in R3, and the next problem will be something else, right? So you're kind of, you know, doing this study of vector spaces with these main examples in mind. Within these vector spaces, however, we have subspaces. And you want to be able to decide yes or no if a set forms a subspace or not. So, you know, this is a classic example. Is S a subspace of V? Okay, and it's a yes-no question. And if you get something like that on the test, which I almost guarantee you will, you should really just take a breath and think about it first, because it's a yes-no, and the thing is, if the answer is yes, you're going to proceed one way to write down your solution. And if the answer is no, you're going to do something totally different, right? And so you don't want to just start sort of mindlessly trying to move forward with this until you have a pretty confident idea about whether the answer is yes or no. So as a illustration of what I'm talking about, so for example, if there's no zero vector in the set, if the zero vector is not in S, then the answer is no. For sure, the answer is no. Okay. On the other hand, if S is a span of something, if S is the span of something, then for sure the answer is yes, right? So there's some fast situations where you can say no. There's some fast situations where you can say yes. Another one that's a fast yes is if you have a null space of a matrix. So if somebody gives you a matrix and you're looking at the null space of that matrix, guaranteed for sure that then this is a yes. And you can just justify it really quickly. So if you have a null space of a matrix, you can skip checking closure under addition and scalar multiplication, and you can just simply state this fact that a null space is always a yes, right? By the way, we just recently were talking about row space and column space. Those are both expressed as the span of something, right? The row space of a matrix is the span of the rows of that matrix. That's a subspace. The span of the columns would be the column space. That's also a subspace. So we have those very familiar examples where you can just say yes right away. Now, I'm probably going to ask a follow-up if I can. If the answer is no, I really can't. If the answer is no, it's like, all right, I guess there's no subspace. We can't really do anything. But if the answer is yes, I might ask something like, give me a basis, give me the dimension. So I guess I need to add that to this list here. So basis and dimension, you need to be able to calculate the dimension of a space and find a basis. Remember that a basis is a spanning set that is also Li. So linear independence and spanning sets are very closely tied in with having a basis. And my favorite question to ask is not, is such and such a basis? Usually what I'll do is I will give you a set and I will ask you, is whatever the set is here, Li spanning set both or neither? And we've practiced this in our group work quite a bit, and certainly there have been a lot of problems where I've given you a set of vectors and I ask you which of these things is true. Okay, so that's something to keep in mind as well. That spanning sets handout that I gave you guys really is worth digesting again. The idea is that I might ask you to find a spanning set for something, or I might ask you, is something a spanning set? Those are the two main questions that anybody would ever want to know, right? So, and same thing with linear independence, right? I give you this set of vectors, I want to know, are they linearly independent? If they're not, if they're LD, I might ask you to produce a linear dependency for me and or remove the linearly dependent vector so that you're down to a basis, if that makes sense. So you guys remember that we did an example like that in class. Let me see if I can find the example of this. You know, so if you have a set of vectors, let's say it's not a basis, I might ask you to tweak it so that it becomes a basis, either by removing linearly dependent vectors from the set, or if it's the opposite problem, I might have something that doesn't yet span the space. I might say, give me another vector so that my collection does span the space, you see. So I could do something like that. So basis and dimension, this is going to be huge. Like this is like an absolute core idea of vector spaces, is basis and dimension for sure. What other things do we have? Well, I already mentioned briefly the row space, column space, and null space of a matrix. All of those are important to know. That recap summary handout is everything you need to know is on it in that little table. You just have to learn that table really, really well. For example, the row space is a subspace of Rn. So if my matrix is M by N up here, right, the row space will be a subspace of Rn. The column space will be a subspace of Rm. And the null space will be a subspace of Rn again. So you have to get the M and the N in the right place. Okay, which one is a subspace of which one? So this is an M right here. Subspace of Rm. Okay, so we have that. One thing that's a little bit strange is that the dimension of the null space is called the nullity over here. But the dimension, so these are the dimensions. So the dimension of the null space is called the nullity. The number of pivots is the dimension of the row space, which is the rank, and it's also the dimension of the column space. It's interesting that both the row space and column space have the same dimension, but one of them is a subspace of Rn, and the other one is a subspace of Rm. So these are two equal-sized, equal-dimension subspaces, but they're subspaces of different things. And that can be a little bit hard to wrap your mind around sometimes. But anyway, so that's just something to keep in mind. Don't forget the very important rank nullity theorem. So the rank of a matrix plus the nullity of a matrix adds up to n. N is, of course, the total number of columns in the whole entire matrix, like that. So that's something else that you want to know. So okay, and then there's the invertible matrix theorem revisited. I didn't do this yet, did I? This is something I'm gonna briefly go over on Monday. It's just that list of statements for invertible matrices that we started back in September. We can now add a bunch more things to that list. So I'm gonna do that. Well, maybe I'll do it later in the review as well. It's not anything that's that hard to go over. Okay, so let's do some problems. Are there any questions on the overview? This overview was deceptively brief. This is a big chapter, right? There's a lot of stuff here, so it takes a little while to kind of get the hang of it. So let's try some examples. Do you mind if I start with a couple of theoretical examples? Maybe that would be good if I can find them. Yeah, let's try some theoretical examples. So here's an example. Prove, and I'm going to give you actually two examples here. So part A, if A is an m by n matrix with call space of A equal to the null space of A, right? Then m equals n. Does anybody have a... When I say prove, I really just mean explain. Like I want to know, like, why would this be the case? If you have a matrix whose column space is the same as its null space, so I kept this up here on purpose, didn't I? So the column space is this part right here, and the null space is over here. So imagine that the column space is equal to the null space. Yeah, go ahead.
Would it be because the subspace of Rm would be equal to the subspace of Rn?
Right, I mean, exactly. It's basically because of the equality here. The idea is, so there's nothing really bizarre here. This is just because, look, the column space, every vector that's in the column space has m slots in it. Every vector that's in the null space has n slots in it. This set of vectors is being assumed equal to this set of vectors. So if you have vectors with m slots that are the same set as a set of vectors with n slots, then that number of slots has to be the same. So we just have to write that down, okay? So let's just say that since the call space of A consists of vectors in Rm, and the null space of A consists of vectors in Rn, then m equals n. You could just say something like that. You could express it in different words if you wanted, but this is the gist of it. There's not a whole lot to say there. Does that make sense? Pretty easy? Okay, let's try another one of the same kind of nature. Part B here. If A is an n by n matrix, so this time I have a square matrix, an n by n matrix with the row space of A equal to the null space of A, if the row space of A is equal to the null space of A, then A cannot be invertible. Okay, the row space is equal to the null space. That's certainly feasible. This is a square matrix, so all of the subspaces of whatever are all the same. N, N, and N for all three of those subspaces. Let's imagine that the row space and the null space are the same. Then I'm claiming that A cannot be invertible. Does anybody have any ideas why?
Would it be because of that formula that you have there, the rank of A plus the nullity of A equals N?
Aha! I like it. So this is what you want to look at. What is the, well, if A was invertible, what would its rank be? N, right? Remember, an invertible matrix has full rank. So if A was invertible, let's just see what would happen here. If A was invertible, then its rank would equal N. And if its rank was N, then what would its nullity be? 0, right? According to our rank nullity theorem. This is just a nice little problem that kind of puts this together. So if A was invertible, it would have a full rank of N, so its nullity would be 0. And what's wrong with that? It doesn't equal 0, why not? So how do we use this part? Like, this is the assumption, we haven't mentioned this yet.
Oh, because the rank and the nullity wouldn't be equal.
Right, the dimension of the row space is the rank. The dimension of the null space is the nullity. We're saying that they're equal. Okay? So, however, by the assumption, the rank of A is supposed to equal the nullity of A, because the row space and the null space are the same. And now you see the problem is that, well, N is therefore equal to 0, and that's obviously a contradiction. So this is impossible. I'm kind of out of room here, but I think you've got the idea. So this then becomes impossible at that point. Does that make sense? People kind of get that? Okay, great. So that's just a couple little theory problems about the rank, the nullity, the row space, null space, and column space. You guys are still working on some homework, right, for that section on 4.8, 4.9, and so on. Okay, let's do some actual subspace examples here. Let me come back over here. I'm gonna pull a couple of problems out of the book. I felt like the homework on subspaces, some of the write-ups were a little bit, off track. So it might be good to practice a little bit on this. So let's do a few examples on this. So is S a subspace of V? And then what we'll do is we'll do several examples and we'll try to prove them. So for the first one, I'm going to use C of 0, 1. So that's V. V is C of 0, 1. And then let me take S to be the set of functions f in V such that f of x, such that 0 is less than or equal to f of x is less than or equal to x for all x. Okay, so we'll practice with this example real quick. So what is this actually? This is my vector space is just all of my calculus functions. I'm thinking of the domain from 0 to 1 right here. So it's just everything that I could graph that would be, you know, somehow on here. Somehow with a domain at 0 to 1. Okay? This would be what V is. All calculus functions with a domain at 0 to 1. Now my question is, if I take only those functions where the function is between 0 and x, would that form a subspace of V? No. If you're not sure where to begin, I would start with the 0 vector. Now what is the 0 vector? The 0 vector is just the function, in this case, the 0 vector is just this function right here. Right? It's just the function y equals 0 basically. Now, is that function in S? Is it true that this function has the property that 0 is less than or equal to the function, which is less than or equal to whatever the x value is? By the way, the x here is just forms just this line, right? Y equals x. So is it true that the 0 vector is in S? Sure is. So the 0 vector is definitely in S. It's just helpful to write that down. If for nothing else, you can get some partial credit because you'll be showing me that you remember the 0 vector check. This is the 0 vector check. This function that is just sitting on the x-axis is definitely in S right here. Okay, so now we have to think about, if it passes the 0 vector check, then we have to start thinking about whether we believe it will be closed under addition and scalar multiplication. So some pictures might help give you the idea here. So if this is 0 and 1, and we're saying that, so this is the line y equals x, let's say. What we're saying is that our function has to stay between 0 and x. So the functions that are in S are just the functions that are in here, right? It's things like that. They have to stay kind of sandwiched in there. And the question would be, okay, if you took 2 of those and added them together under addition, right, would the function stay under that line after you add them together?
No.
Don't think so. Okay.
Or I just saw it easier with like
Scalar multiplication, right. So would it be true that if I took one of these blue curves and scalar multiplied it by a number, that it would stay sandwiched in this interval, and you don't think so? Okay, I agree, and I actually also agree that it's easier to just talk about the scalar multiplication. But see, I have not written anything down yet beyond the 0 vector check because I'm thinking it through first. The way the write-up looks, if it is a subspace, is very different from what you're going to do if it's not. And so it's a good idea to have a thumbs up or thumbs down on this example before you start launching into a write-up. So if we think that something is not going to work, now we can address it. So closure under scalar multiplication fails. And what I would recommend that we do is create a counterexample. When something is not true, a specific counterexample is always the best thing. Can somebody give me an example of a function that they know that would be sandwiched in here?
X squared. Are you going to just do y equals x?
We could actually just do y equals x. So this goes up to 1, 1 right here, by the way. We could just do the line y equals x itself, or we could do y equals x squared, which would be like that, right? Or there's other things you could choose as well. So let me just take the example y equals x. So let's let f of x equal x. Okay? Then f is in S, because obviously if it equals x, then it's less than or equal to x. Okay? However, okay, what scalar multiple do you want me to use? 2. You have to choose a specific one. Don't just write k here. Actually use a specific one. So 2 times f of x is now 2x. The function 2x is unfortunately going to be over here, right? It's going to be a steeper line that is above the line y equals x, and this is not in S. So that's it. You have shown that you started with a function in S, but 2 times that function is not in S. And you could just say that and move on. Okay? Okay, great. So that's a good example. Let's try another one. A completely different example. Let's let V be M2 of R. And let's take S to be the set of capital A element of V. Notice how I'm trying to use notations. Like here, I was working with a vector space of functions, so I called my vectors F. Here I'm working with matrices, so I'm using a capital A for that. Okay? And then the condition here is going to be all entries of A are non-zero or A is equal to the zero matrix. So we're going to take the zero matrix together with all of the matrices where there are no zeros in the matrix. So let's think about that. Do you understand what the set is? The set S has the zero matrix in it, and it has any other matrix in it where all of the entries are not zero. Do you think that that's going to be a subspace? Let's start with the zero vector. Okay, so the zero vector is, of course, this one. Is this one in S?
Yes.
It's pretty much given to you right there that that's in S. Okay, so we put a check. We did the zero vector check. So now, what about the closure under, so if I add together 2 matrices that have all of their entries not zero, would the resulting matrix have to have all of its entries still non-zero? No, it would not, right? And so and that would be under addition. Actually, on this one, the scalar multiplication works. If you start with a matrix that has no zeros in it and you scalar multiply it, you'll either have no zeros in it or you'll end up with the zero matrix if you chose 0 as the scalar. So, but still, if even one of these axioms fails, then the whole thing fails, right? And we can just kind of go on. So closure under addition is going to fail on this one. Okay. So let's think about how to justify it. I need an example. A specific example would be the best, right? A specific example. Can somebody give me
One.
1, 2, 2, negative
1, 2, 2, negative 1. Okay, we'll make that matrix. And then we need another matrix B. Anybody have a suggestion what we could use here? We're trying to make this not work.
Negative 1, 0, 0, 0.
Negative 1, 0, 0, 0. I love it. Oh, except I can't do that. Because all of the entries have to be non-zero. So I don't love it, sorry. Negative 1, 3, 4, 5 or something like that? Okay, let's try that. So both of those are in S. So we'll just say that A and B are in S. And then I'm going to look at A plus B. A plus B, when I add them up slot by slot, the upper left corner becomes 0. And then I get a 5 and a 6 and a 4, right? And that matrix, it's not true that all of its entries are non-zero. And so this is not in S. Guys, you must write this down. This last part is critical, that it's not in the set. So just be sure not to forget to follow up at the end. Okay, so the result is not in S. So closure under addition fails in this case. Does this make sense? So these are two good examples. They're kind of different. This one, the scalar multiplication, was a little easier to address. This one, the addition, was a little easier to address. Let's do another one. Let's do another one. Let's do the set of, sorry, so V is P3 of R, and S is the set of P of X, an element of E. Notice I'm going to use a P of X here because I'm talking about polynomials, such that P prime of 2 is equal to 0. Okay, so these are just all polynomials whose derivative, when I plug in 2 as an input, is 0. It's all polynomials that are flat at the point x equals 2. Well, I'll start with the 0 vector. My 0 vector in this case is just 0, right? It's the polynomial 0. If you take the derivative, so is 0 in this set?
Yes.
So if we take P of X equals 0, that implies that P prime of, well, the derivative of 0 is just 0. And if P prime of X is equal to 0, then that means that P prime of anything that I plug in for X will be 0. So this implies that 0 is an element of S. This is just a little bit of a verification of that right there. Okay, so the 0 vector is in S.
I thought it would have to be like a third degree polynomial.
Well, the thing is, no. Remember that this is this one, right? This is the set of polynomials of degree less than or equal to 3. So for example, when I write 0 here, what I'm really writing is 0 times x cubed plus 0 times x squared plus 0 times x plus 0. That's actually what that is. Right? Does this make sense? Okay, so that polynomial is in the set. Okay, so then what about closure under addition? What do you guys think? You think it'll work? If I take two polynomials that both have a derivative of 0 when I plug in 2 for x, then when I add those polynomials, would that still be true? I think so. yeah, this is going to be true. The closure under addition is going to hold, and we just need to justify it. So now we have to actually work on the write-up a little bit. So to write this up, how am I going to start this off? Let f of x and g of x be elements of S, right? So we take two things that are already in S. Do I need to write them out, ax cubed plus bx squared plus cx plus d? The reason that I don't need to do that is because my condition here doesn't do that. If this condition had been expressed somehow in terms of like the coefficients of the polynomial or whatnot, well then I would need to write these out in terms of cubic term, quadratic term, linear term, and constant term. But because of the simple nature of the way this condition was stated, I'm going to be equally terse over here and equally brief over here. Okay, so let's write down what this means. As soon as you're telling me that something is in S, I want to know, what does that tell me? Well, this means that f prime of 2 and g prime of 2 are both equal to 0. Okay, and what I want to look at now, thank you. Thanks. What I want to look at now is f plus g. The question is f plus g in S? Well, it just means I have to take the derivative of it and plug in 2. Okay, so then let's look at f plus g. I'm going to take the derivative of it and plug in 2. Okay, now what is that? How does that break down? Exactly. The derivatives respect addition, right? So if I want to add the derivatives individually, I could certainly do that. This is just the derivative of f at 2 plus the derivative of g at 2, which is 0 plus 0 by assumption, and that therefore is 0. Now, one thing to be a little careful about here, don't write element of s here, because you're not trying to tell me that 0 is an element of s. What you need to do is come over here and write one more thing. F plus g is an element of s, right? The condition for that has been checked right here. And then we're just drawing the conclusion on the last line. Does that look good? Okay, great. Let's look at the closure under scalar multiplication here. Okay. How do we write up the first part of the closure under scalar multiplication? Let f be as above, and k is a real number, exactly. So we take a real number and we take f as above, and we're just going to look at k times f. So k times f, I have to take the derivative and then plug in 2. Right, so I'm going to do this calculation here. Okay. Well, when you take derivatives, what can you do with constants? Always pull them out, right? So you can just pull it out, so the k comes out in front, and then you're taking just the derivative of f prime of 2. Well, f prime of 2 was 0, so this is just k times 0, which is 0, right? Because we got 0 there, thus k times f is an element of s. Right? K times f is an element of s. All right, fantastic. So we've got that. So this one is a subspace. If you really want, I would recommend. I probably wouldn't take off for this, but it would be good to do it. You should probably conclude that thus S is a subspace of V. Just to kind of tie it all together at the end. Okay, so now I have a follow-up. I didn't get to do a follow-up on the others. If they weren't subspaces, we're done. They can't do anything else. But now we have a subspace, so I have a follow-up question for you. I want to find a basis and dimension for S. So find a basis slash dimension for the set S. Let's see if we can do that. Since we have a subspace, we know we can do that. Okay. So I need a spanning set that is linearly independent.
Doesn't that only augment it with number signs or zeros?
If we have a proposed spanning set or a proposed basis and we're wondering, is it a basis or not, or is it Li or not, or is it a spanning set or not, then I would put those vectors in the columns of a matrix and I would augment it appropriately and follow my calculation to figure out where my pivots are. But here we don't even have any vectors in our hands yet to do that with. So we might get to that point, but before we can get to that point, we need to figure out, well, what are the, proposed basis vectors that we're looking at. So this is the find a basis question. This is not asking, is something a basis? We're being asked to make it for ourselves and to create the basis for this set. So I'm wondering if anybody has any ideas here. Turns out that to do this, and we haven't done a lot of these yet, so it's not something that you have had a lot of practice with, but what you have to do here is actually go back now and write your polynomial as ax cubed plus bx squared plus cx plus d and start working with it that way. I know that to show that we had a subspace, we didn't need to do that. Nowhere over here did I ever have to write out terms of my polynomial, right? But to do this part of it, I'm going to want to do that. What I'm going to do is I'm going to write p of x as ax cubed plus bx squared plus cx plus d. I'm going to write it that way. Now what I know is that this is supposed to be an element of S. So this is a polynomial that is in S. What that means is that if I take the derivative of this and then plug in 2, I'm supposed to get 0. So let's just do that. So then if I take the derivative, p prime of x, okay, everybody just has to do their calculus power rule here, right? You get 3ax squared plus 2bx plus c. And then I'm going to evaluate that at 2. So p prime of 2 is going to give me 12a plus 4b plus c, and that is going to have to be equal to 0. So 12a plus 4b plus c equals 0. Okay, so let's come back over here. That actually gives us a constraint. Not every polynomial in P3 of R is going to be part of S. Only those polynomials that meet this condition. So the point of this is that I have actually 3 free variables. What are the 3 free variables that I have in this equation? No. The 3 free variables. So if we just kind of label this way, so the 12 is with the A, the 4 is with the B, 1 is with the C, but there's another variable. D. D, right? The D has actually disappeared from the derivative because it was the constant term, right? But this is the augmented matrix for the linear system, if you can call it that. It's not really a system, it's just one equation, right? But your pivot is over here, right? Your pivot is on the A variable. So what I'm going to do is I'm going to think of B, C, and D as the free variables. I'll call those R, S, and T. And then I can figure out what A is by solving this one, right? So what is that going to give me? Negative 1/3 of R minus 1/12 of S, I believe. Right? Is this making sense? Yeah. Now, a big temptation with this, what a lot of people are going to want to do, you guys aren't, but a lot of people will do this, is they will then put this into a vector. So don't write this down. They will put this into a vector like this. 1/3 R minus 12S, and then RST. They'll do that, and then they'll bust out the variables and write down an answer that's, you know, got some columns like this. And say, there's my basis. Well, these would be a spanning set for all of those vectors, right? But what's wrong with this, all of this over here?
We haven't checked for how long.
We will. We will. But the problem with doing this, guys, is that you're actually writing things like as if they are in R4. Do we have R4 anywhere in this? No, this is not a problem about R4. There are no slots. We're talking about polynomials. So what we should do, instead of this, what we need to do now is go back to P of X, which is this expression right here, and plug in the A, B, C, and D that we just found. Okay, so let's do that. So P of X is what? Negative 1/3 of R minus 1/12 of S. That's times X cubed. Okay, let me just clear this out. And then the B term is R, so Rx squared. And then S times X, and then plus T. So we actually just want to feed in the A, B, C, and D into our polynomial. And now we can still bust out the variables. It's just we don't have the slots, right? So I can still take this thing and pull out the R. So I'm going to look, where's my R? Here's the R. I have a negative 1/3 X cubed on it. And then here's an R with an X squared. Okay, so we get negative 1/3 X cubed plus X squared. And then we do the S term. S is being multiplied here by negative 1/12 X cubed, and then plus X. Okay, and then I'm going to do the T term. The T is just multiplied by 1 at the very end. Okay, so with that in mind, guys, what is my basis? Isn't it just the vectors that you've busted out?
Yeah.
That's it. You just have to write those into a list. Exactly. So we're going to get 1, and then negative 1/3 X cubed plus X squared, and then negative 1/12 X cubed plus X. Okay. Now, just a quick comment about that. So pretty clearly these are a spanning set, because every polynomial P of X that was in the set S was expressible as a linear combination of these three. That's pretty clear. The issue you might wonder about is linear independence, making sure that these vectors are Li. So this is where we could do what kind of, Coco, what you were suggesting is we can take these polynomials, put them now into columns of a matrix, augment with zeros. Remember, when you're checking linear independence, you're going to augment with a column of zeros. And then we can do some EROs and whatnot, right? So for example, what I could do to check Li right here, they already are a spanning set. No need to justify that. That just comes from this calculation here. Okay, but if I want to check Li, that first polynomial has a constant term and no other powers of x, right? The second one has no constant term, no x term, 1 on x squared and negative 1/3 on x cubed. And the last one has no constant term, 1 on